So in particular, I'm just going to write down the ones that will be relevant for the mass formula. So I have alpha prime, p left squared over 4, plus sum over oscillators, n equal 1 to infinity, alpha minus n, alpha n. And then I have equals to prime, p right squared over 4, sum n equal 1 to infinity, alpha minus n, alpha n. So now, so the mass of the string, right? So m squared equals to L naught plus L naught tilde plus a normal ordering constant. And so this is something that you did. One of your homework assignments was to compute the spectrum of the string in the case when omega was equal to 1. So here I'm just gonna, you can go ahead and do exactly the same analysis, and I'm just gonna write down the answer here. So you will find out that m squared takes this form, n squared over r squared, plus omega squared r squared over alpha prime squared. And then there is plus 2 over alpha prime, and plus n tilde minus 2. So that's the expression for the mass spectrum of a string. And then remember that when we derived it in class, we did a light quantization of the string. We didn't have those two conditions, but we just had the oscillators. Well, actually, but additional conditions that we had the level matching condition, which was that n minus n tilde was equal to 0. And this level matching condition was when we insisted that there is no origin on a closed string, right? So then we constructed the corresponding generator of a translation along the segment direction, and we asked that the physical states are being manipulated that led to a level matching condition. So in our current case, the level matching condition is going to be modified. So once we have momentum and a winding for our strings, there is an additional contribution n times omega. Okay? So this is, there are again various ways to do this. So strictly speaking, the only way how we learn in this course how to do this analysis using the light quantization, something that you did in the homework assignment. Okay. So let's look at this mass formula. And try to identify different pieces. So this contribution, right? So this is an analog of Kaluza-Klein tower in quantum field theory, right? So those Kaluza-Klein massive states. And those are the guys that were charged under U1, right? So remember that there is a mu, which is the U1 gauge symmetry, okay, after we do a reduction on the circle. And so those are the states that carry n units of charge. So this additional contribution is also very easy to understand intuitively. So this contribution comes simply from the states of the string, which simply winds around the circle, right? So if I compute the energy of the string, so that winds omega times. So the energy of the string is the tension of the string times 2 pi times omega, right? 2 pi r times omega. And the tension of the string 1 over 2 pi alpha prime, and then I have times 2 pi r omega r. So this is omega r over alpha prime. So the second square, the contribution to the mass square is simply the contribution, kind of the minimal energy that is required for a string to wind around the circle. And there is a non-zero energy because the string has a non-vanishing tension. So the remaining contribution as before, this is just contribution transfers oscillators of the string. Okay? So that's exactly as we've seen before. So once we have a formula for the mass and we have a level matching condition, we can ask our next question. And our next question is the spectrum. The spectrum. Well, the first, what is the lowest lying state? So the lowest lying state corresponds when I choose n equals omega equals to n equals n tilde equals to 0. So notice that the level matching condition is obviously satisfied in this case. And so what we have is that n squared equals minus 4 over alpha prime. Okay? So that's our tachyon, right? So once we compactified a string on the circle, we did not get rid of a tachyon. So the tachyon is still there. So tachyon. As before. Right? And so the tachyon is the state. So now if I think about state corresponding to tachyon, it can have a momentum. So this is a ground state of the transverse oscillators. That's why I put 0 here. But it can still carry some momentum, right? So this is a state in the Hilbert space corresponding to a tachyon. So the next we'll look at the massless states. So we'll look at massless states. So what are the massless states that we have? Well, so we have to impose a condition n squared equals to 0. So for generic value of r, right? For generic, by using the word generic, I mean almost any value of r. For generic r, what we have to do in order to get massless state, we have to put n equals omega equals to 0, right? And then n plus n tilde minus 2 must be equal to 0. Right? So that will give me massless states. Now, the level matching condition, when n and omega equals to 0, the level matching condition simply tells you that n must be equal to n tilde. And so in order for me to look at the massless states, what I must have, I must excite a single left-handed oscillator and a single right-handed oscillator. And so the way I can now do it is the following. So I have alpha minus 1 mu, alpha minus 1 tilde mu. So I'm exciting left and right-handed oscillators. Remember that those oscillators carry a space-time index, right? So before I would put m and n, so here I have to decompose it. So I can mu, okay, acted on a vacuum. So that's one state. Then there is another way how I can construct massless modes. So I can excite a mu oscillator on the left, and I can excite a 25th oscillator on the right. Okay, so the 25th direction is the one that I compactify on the circle. However, what I want to do, I want to right. So if I want to decompose it under nice transformation with respect to space-time, leftover space-time Lorentz transformations, then I can write it down in this way. So 25, okay, so this is minus 1, 25, so minus 1, 25. So I have to symmetrize pretty much left and right movers. Minus 1 further. So that's another state. Okay. And you will see in a second, it will become obvious why that's the right thing to do. And then finally, there is one more. So there is a symmetric combination and anti-symmetric. I could have left it like this, right, and then wrote additional one, but I choose to symmetrize and anti-symmetrize it. So then there will be alpha minus 1 mu, alpha minus 125 minus alpha minus 125, alpha minus 1 tilde mu. And then there is one extra, and then there is one extra state. And so this extra state is going to be alpha minus 125, alpha minus 125 will active on the vacuum. Okay, so we enumerated all the possible master states that could be there. And so now it becomes actually clear why did I do the decomposition with respect to plus and minus, right? So what do we have here? So here I have a G mu, right? So I have a graviton in little d dimensions, right? In 24 dimensions. Plus I have a d-dimensional dilaton. I have a scalar, which will be just a trace here. And then I have what we call an antisymmetric tensor B mu tilde, right? Now, this part, this is a symmetric combination. This is symmetric combination that carries one space-time index. So this is a vector, right? But because it's a symmetric combination, so this guy comes from GMN. It comes from the metric in 26 dimensions, right? And so this must correspond to our field A mu, the vector field. Now, the antisymmetric combination obviously comes from antisymmetric rank 2 field in 26 dimensions, and so this is what, when we did our Kaluza-Klein reduction, we denoted as A mu prime. And so finally, this additional scalar field plays a role of sigma. Okay, so we identify, once we restrict to this sector, when n equals omega, n equals to 0, there is no momentum, no winding, we get exactly the same spectrum of states as we obtained once we took gravitational action for the bosonic string and we did Kaluza-Klein reduction on the circle. So this everything that we did here, analog of QFT. And so we recover exactly the same spectrum. And if we write down the effective the equation of motion, we will get precisely what's obtained by Kaluza-Klein reduction. All right, guys. However, here there is something that I'm just going to mention. I'm not going to derive this or discuss anymore. So remember that n was a charge under A mu, and I was complaining that there is nothing that's been charged under A mu prime, and so now if you do carefully the study of massive states, right? So now there are two types of massive states that happen in string theory in the CFT. So one is the momentum massive states, and those are the ones that will be charged under A mu. But there are also winding states. So it turns out that those winding states, omega is a charge. Under this additional vector field that comes from antisymmetric rank 2 tensor. And it's clear why now, once you take this for granted, it's obvious why there is no way how you could have seen those charged states in quantum field theory, because those states are non-local. Right? So those charged states are the states where your object must wind around their compact direction, and there are simply no states of this type in local quantum field theory. That's why there was an intrinsic asymmetry in the string theory, but this asymmetry is being alleviated once we go to a conformal field theory. So here, so one thing that I want to mention. So if I am, remember that there is an operator state correspondence. So in order for me to construct this vector boson, what I have to do, I have to act with creation operators on a tachyonic vacuum, and then I will create a massless state. But I can ask the question, what is the operator corresponding to this state? So using operator state correspondence, so the state corresponding to a gauge boson is del x mu, del bar phi plus or minus del bar x mu, del x 1 over. And then I have e to the I dx. Okay, so everything so far is exactly as according to Planck-Nicolson. So what exactly the string theory tells us something new happened? Well, actually, for arbitrary radius, nothing new happens. However, there is something very interesting happens for a particular radius. So there is a special radius. There exists a special radius. And so this special radius equals alpha prime to 1/2. So the radius of the circle equals precisely the string length, right? So this alpha square root of alpha prime gives you a string. So if I substitute that in the formula, then my mass formula takes the following form: m squared equals to 1 over alpha prime, and then what do I have? N squared plus omega squared plus 2 m plus n tilde minus 2. And of course, I still have to have my level matching condition plus. I'm going to use the same notation as before. Here's my level. Plus n minus n tilde plus n minus n tilde equals to 0. Okay, so again, what we are doing, remember that at this stage, the radius of a circle is arbitrary. So as long as we study what is the massless spectrum of my string theory for arbitrary radius of a circle for generic value, we will get exactly what the field theory will tell us. Now I am saying let's look at the special radius, right? So the size of the radius is precisely the string scale. So the mass formula changes to this. Now what I can do, I can solve for n tilde from the level matching condition. So I will find that n tilde equals n plus n omega. And so if I ask the question, what are the massless states? M squared equals to 0. I'm just going to substitute it into this expression. So what do I have? I have n squared plus omega squared plus 2n plus, instead of 2n tilde, I will substitute 2n plus 2n omega must be equal to 4. So on this special circle, the massless mode satisfies the following condition: n plus omega squared plus 4n equals to 4. Okay? And remember that n and m, they are integers. Okay? So now you can immediately see that in addition to the massless states that I discussed before, there are new massless states. Okay? So what are those new massless states? I have to solve that equation in terms of integers. So the new massless states, well, so there are two types. So one, I can choose capital N equals to 0, and so then that tells me that m plus omega squared must be equal to 4. So the states that I have, and omega is +1, +1, -1, and -1. So those are additional states in the spectrum of my compactified string theory that will end up in masses. Okay, so let me complete this table. So I have +1, +1, -1, -1, and right. So here I'm going to write n. So in this case, capital N equals to 0, and then I have n tilde. So I can use the formula in that for this states what is the value of n tilde. Remember that n tilde is given by the level matching condition. So in this case, I will find that n tilde equals to 1. Okay. And so that's one possibility. If I put n equals to 0, then I have this condition. But there is another way how I can get massless states. And I say that this n equals to 1. So in this case, little n plus omega must be equal square must be equal to 0. And so there are two more solutions that I can find. 1 and 1, so those are 1 plus 1 minus 1, and minus 1 plus 1. Okay, so in this case, n tilde is 0, 0. Okay.
How about the solutions omega is equal to 2?
Right, very good. I wanted to ask exactly this question. So n equals plus 2, omega equals minus 2. So what about those? Somebody can tell me why?
N equals 2 is not so interesting.
Look, I mean, we're doing string theory, so the questions of being interesting is we have to be right. We have to be very precise, right? We cannot again.
So it's
one of the
energies.
no, we cannot. Again, see, at this stage, I'm not making any approximation, right? I'm just asking the precise question: what's the spectrum? What's the spectrum of the theory? And you're absolutely right. I mean, I can solve that equation in integers with n and m being equal to, 2, 3, 5, 100. What's the problem with that? Can somebody tell me? Okay, let's see what the problem with that is. So let's choose your favorite state, which is 2 and minus 2. For this state, what is the value of n tilde? So the value of n tilde, I have to look at the level matching condition, right? And so n tilde is going to be equal n plus n times omega, right? So n in this case equals to 1. So I have 1 plus 2 times minus 2 equals to minus 3. That answers your question, because there is no way I can excite minus 3 oscillators. I have a ground state, and so the only thing I can do, I can excite only a positive number of oscillators, right, on top of the ground state. That's why, so there is a constraint that the oscillator numbers must be positive, and that restricts only those states. Okay? So now I can ask the question. So there are these additional states. What those additional states correspond to, right? What does the vertex operator corresponding to those additional states? And to answer this question, right? So first of all, I'm going to write it down here, the answer, what the operator corresponding to the state. But I want you to see what the answer must be. So what you are doing here, you are exciting an oscillator. So this is left-handed oscillator. This is a right-handed oscillator. So when you excite one left-handed oscillator, how many different ones you can excite? 24, right? Because those are exactly, those oscillators that you are exciting are the ones alpha minus 1 to the mu. So the oscillators that you excite, they will carry a space-time index. So those are the guys that will be vector bosons, right? So those are vectors. So all these states are vectors, and those guys are also vectors. So here, the index mu is carried by left movers because you are exciting a left moving oscillator. And here, the states that you are exciting are right movers, right? So the vector index is carried by right movers. So the states up here, those states, okay? So I will call them group 1, those guys, up 2. So the states in 1, so they have their vertex operator L mu, right? So that corresponds that I'm exciting one left moving oscillator, and you can see explicitly the space-time mu index. And then I have to excite appropriate combination corresponding to n equals plus 1 or minus 1. So it turns out that this is e to the plus or minus 2 pi alpha prime to the 1/2 x left 1/5. Okay. So in the second case, so this guy depends on z, and this guy is z bar. So here I have del bar s e z bar e to the plus or minus 2 pi alpha prime square root. Sorry, this is x, right? So this is x left, 1/5 of z. Okay, and then so we still to z pi in those cases. Good. So what did we find? Right. So in quantum field theory, right, when r is not equal to alpha prime to the 1/2, there were 1 plus 1 gauge bosons, right? Those are the guys that we are transforming under U1 cross U1 gauge symmetry. And we simply understood the origin of this gauge symmetry has come from simple Kaluza-Klein reduction. So what we are finding here is that at a special radius, there are additional massless gauge bosons, and there are precisely 4 of them. Okay. So at r equals L string, 1 plus 1, the number of gauge bosons goes to 3 plus 3. Okay, I wrote it explicitly 3 plus 3. I'm not gonna, in order to derive the statement I'm gonna make now, require studying interactions, but when you do it, you will find out that, so these additional gauge bosons will correspond, once you turn on string interactions, will lead to an interacting gauge theory. And what will happen is that you will end up having an enhancement of the gauge symmetry. So the gauge symmetry from U1 cross U1 will get enhanced into SU2 cross SU2. So you get a non-abelian gauge theory at a special compactification radius in string theory. Okay. So in fact, so when the radius is equal to precisely L string, you get additional massless gauge degrees of freedom, and then they will complete the gauge multiplets, right, for the SU2. The SU2, you need exactly the dimension of the adjoint representation is 3, so you need three gauge bosons here. right? And you need the 3 gauge bosons here. So those, the additional states that you're finding there, when you turn on the interaction, you will find out that they describe the interaction of SU2 cross SU2 gauge series. But if you move away, right, so if R is approximately equal to a string, but it's not equal precisely to it, what is happening is that this 4 gauge boson, they get mass, okay? So they're massive, and their mass will be actually very close to 0, depending, so the mass, so 4 gauge bosons, these 4 gauge bosons are massive, and the mass, m squared, is proportional to R minus alpha prime 1/2. So the mass vanished. The mass vanished exactly at the point, but you can make them arbitrary light. So in fact, what is happening here is a string realization of the Higgs mechanism, right? So how does the Higgs mechanism occurs in the gauge series? You guys know? I don't want to go into details if you don't know. But do you?
Tell us. I mean, what is going to be?
Okay, so I just wanted to say that it's going to be exactly as in the gauge series. So what happens in the gauge series? There is you have a charged field, right? And the charged field develops a wave. So when the charged field develops a wave, it will give a mass. It will give a mass to some of the non-abelian gauge bosons that you begin with. And that once those guys get a mass, the gauge group is reduced because only massless gauge bosons can participate in gauge symmetry. So remember that there was a scalar. There was a scalar in our discussion, which was a sigma scalar, the one that was changing the radius of a circle. So that scalar didn't have any charge under U1 cross U1. But it turns out that it has a charge under SU2 cross SU2. So it's a charged scalar under this non-abelian gauge symmetry. So what happens there is that as you move from the special radius, it's the same as giving an expectation value to a charge scale. And so what is happening is that this enhanced symmetry at the special radius is Higgs, spontaneously broken by the expectation value for you moving away from the special radius. Okay? So you have a realization of the Higgs mechanism in string theory. So very good. So the last thing which I want to discuss with you is the idea of T-duality. Okay? And I have to say here, so there has been over the last 10 a little bit more years, there has been 10, 15 years, 13 years. There was a lot of understanding about non-perturbative aspects of string theory. How do strings behave with strong coupling? And so that understanding came from the idea of dualities. And if you can pinpoint the point, where does people start understanding dualities? And so that leads to something that we're going to discuss with you now. So once you start asking and thinking really hard about the T-duality, something that I will mention to you, sooner or later you will discover all the rest, as it was done in string theory. So we're going to talk about T-duality in string theory. So before I go into that, let's go back to our scalar field. Right? Remember that we talked about massless scalar field and massless scalar field. In d dimensions, right? And what I told you that it's equivalent to infinite number of massive fields in d minus 1 dimension. Now, suppose that what you are doing, you are observing, you are just a guy who knows how to look at the, you observe, you try to get an idea of what your space-time look like by studying the spectrum, of a scalar field phi, right? How would you know that, in fact, there is, suppose you're a low-energy observer. Would you be able to say that the number of dimensions is not little d, but capital D? Would you be able to say yes or no? I'm asking you what kind of experiment you would have to do in order to
throw the energies.
Exactly. So what you need to do in order to be convinced that, because this is an equivalent description, and the question you are asking is, how can I discover a hidden dimension? Okay, so that's the type of question you're asking. So you're kind of a person that lives at the energies of the massless state, and you are asking, I'm making an experiment, how do I discover this extra hidden dimension? And the answer to the question is, well, what you have to do, you have to compute the spectrum. And if you compute the spectrum and you find out that this energy density is exactly the same as all above, and it goes up to infinity, then in fact what you have an additional dimension. And moreover, you will not only know that you have an additional dimension, you will know that this additional dimension is compactified, and the radius, you will be able to compute the radius of this extra dimension, right? You will be able to compute the radius of this extra dimension once you know the mass gap in C, right? Because the mass gap is 1 over R. Right? So now let's ask the question: what would happen? What would happen if? Let's look at two dramatic situations, right? So suppose the radius of a circle will go to infinity. What will happen? So if a radius of a circle goes to infinity, then it is simply inconsistent to say that you live in little d dimensions, right? So I'm kind of making this chalk larger and larger, and when the radius of the chalk will become larger than the radius of the universe, then actually it's almost the same as living on an infinite plane, right? So what this tells, and look what happens in a spectrum. So if I study the Kaluza-Klein spectrum in this case, what is happening, I'm getting more and more light states, right? So there is an infinite number of states, and precisely in this limit, I will find an infinite number of massless states. Right, massless scalar states. They, of course, will be different because they carry different charge under the Q1 symmetry, but there will be infinitely many numbers of them. So that's one very drastic thing that if we would come to some other universe and we look at the spectrum and we find an infinitely many massless fields, then we would have to say, look, there is an extra dimension. That would be a signature of an extra dimension by simply looking at the spectrum of our receiver. Now, what would happen when I make the radius goes to 0? So if I make the radius goes to 0, what will happen then? This gap becomes larger and larger. And so, if this limit, what I am doing, I'm literally losing one dimension. Okay, so one dimension is lost, and it's lost irreversibly. Okay, the reason why it's lost irreversibly because again, our task, our kind of test of how many dimensions we have is related to how many massless fields we have. Right? We are thinking about dimensions as being compactified, and we are asking how many scalar fields we have that carry charge with respect to this compactification. Good. So now, suppose that what we are doing exactly the same mental experiment, but the universe that we found ourselves is is not the universe that describes by field theory, but it's the universe that describes by string theory. So then the spectrum that we will see is going to be something like this: n squared over r squared plus omega squared r squared over alpha prime squared. So here I'm going to ask the same question, right? So we have this spectrum, and suppose we have a power of change the radius, right? So I'm going to look at two limits. So suppose that r goes to plus infinity. So when radius of a circle gets very large, the Kaluza-Klein modes will get lighter and lighter. So much like in a quantum field theory, as in QFT, we get infinite number of massless states. Okay, so notice that these winding modes will not contribute anything, because as I increase the radius of a circle, it makes more and more energetically costly for a string to wind around it. And so those states are simply disappear. So the test, I will make the same test as I did in field theory, and I will have to make a conclusion based on the spectrum that there is a new dimension opens up. Okay, so and this opening up corresponds with the limit as r goes to infinity. Now I'm going to make another limit, the same limit we did in a string in a field theory, and that's the limit that led to a loss of one of the dimensions. So in this case, what is happening is that Kaluza-Klein modes get very, very heavy, and they disappear from the spectrum. However, notice that the winding mode becomes lighter and lighter, because it costs less and less energy for string to wrap around the direction that gets smaller and smaller. So here I would say that contrary to QFT, we get again an infinite number of massless states. And so, in fact, there will be, if I give you this spectrum, or I give you this spectrum in the limit r goes to 0 or r goes to infinity, you will not be able to distinguish them, right? So in the first case, you have n squared over r squared. In the second case, I have an integer squared over alpha prime over r squared. So I can rewrite this as omega squared over r prime squared, where r prime is just alpha prime, or let me put it tilde, r tilde is alpha prime divided by r. So in other words, there is no difference if I take either zero limit r goes to infinity or r goes to 0 in a string theory. More precisely, in quantum field theory, when you took a limit r goes to 0, you lost a dimension. So here you are losing the kind of dimension corresponding to Kaluza-Klein, but you are restoring a dimension. You are restoring one additional dimension corresponding to the winding mode. Okay? So the number of dimensions stays the same. So if you think more about this, it is not a surprise now that I tell you that there is an exact symmetry in a theory that, that identifies different compactification radii, right? So let's look at a mass spectrum of strings. So I can look at the modes which have momentum winding, and then the modes, and so those are momentum and winding modes on a circle of radius r. And so if you write down a mass formula, including these parameters, so you will get an identical expression if you write down the formula with winding and momentum exchanged, and you go to a new radius, right, which is alpha prime divided by r. So the spectrum of the string theory is invariant under the transformation where you go from a radius r to a radius 1 over r times L string squared. And the only thing you have to do, you have to flip back the winding and momentum mode, right? So this is the same as flipping two U1s that I was mentioning earlier today. So this is an exact symmetry of the spectrum, and actually you can see now that what is this extra dimensions that I was talking about. So here, from this perspective, you are taking a radius to 0, so you are losing one dimension. But in terms of the dual or equivalent description, what you are doing, you are decompactifying this dimension. Because what you are doing now, you are simply treating the winding modes as analog of a Karuta-Klein mode. So this symmetry is known as T-duality. And so in particular, this T-duality tells you that there is a notion of the minimal length in string theory, right? So it doesn't make sense to ask how does my string theory look like on a space that has length L string over 2, okay? Because what you have to do, you just have to convert, so there is a minimal R minimum, the minimum radius in the string theory is just the string size, okay? So anything less than that, I can rewrite in an equivalent language that will correspond to a string theory on a larger radius. Okay? Now, I told you that this is a symmetry of a spectrum, and you can worry, is this symmetry that actually is preserved by interactions, and is this really an exact symmetry in the string theory? And the answer is yes. And in order for me to not exactly prove it to you, but at least justify that that's the case, so remember that the field X, X depends on Z and Z bar, and it's actually a sum of holomorphic left-handed plus and right-handed anti-holomorphic terms, right? So we can ask the question. So we have a Fourier mode decomposition of this of the fields, not exactly this, but del x, right? So del x is equal to something, and del bar x equal to something. So we can integrate it, and so that will give us x left, right? Once we integrate, and this guy will give us x right. And so I can ask the question on the level of of this world sheet field, what is this T-duality that you are talking about? What is this transformation that changes momentum and winding mode? And and you also have to change the radius. And the answer to that question is that what you are doing, you are acting with a parity transformation on the right movers only. So T-duality is a transformation in which x left goes to x left and x right goes to minus x right. Okay. Now, once I told you this, and you can actually, so it goes to this, and then on top of that, of course, I have to change the radius, alpha prime over alpha. So this is z bar. So it's clear that everything is unchanged because for the closed string, and let's concentrate the T-duality as we discuss it right now. We discuss it for closed strings. The left movers never interact with the right movers, right? So our conformal field theory for closed string decomposes into a holomorphic part and anti-holomorphic part. And what I did here, I simply did a parity transformation on the right moving part, which is a discrete transformation on our voltage, right? So that leaves everything invariant. So this transformation leads to the same OPEs and so on. All the local properties, everything is going to be the same. And so in fact, you can also argue that this transformation is preserved by string interactions. I'm not going to go into more details here. I'm just going to mention that one of the ways to argue that is you can shows that this Z2 symmetry, right? So what we have a Z2 right-handed parity. So this Z2 right-handed parity is actually a part of SU2 cross SU2 symmetry on this minimal radius. Right, remember that when we can factify a theory on a radius which is equal to our string, there is an enhanced symmetry. And what you can do, you can actually show that this transformation is a transformation that lies inside the SU2 cross SU2 gauge symmetry. So what this tells you that this is one of the redundancies of the theory. In other words, much like when we talked about moduli group of a torus, right? And we started with what are the space of all inequivalent tori, and we started with imaginary upper half plane, and then we went into fundamental domain, and we said that the physical inequivalent tori correspond only to here. So exactly the same thing. So radius of a circle is a modulus, right? And you have to ask the question, what are inequivalent radii? So what we are finding here is that the inequivalent radii are actually radii that are larger than the string. Okay, so this is not drastically different the notion that when we discussed the inequivalent moduli in a case of torides. Okay, so I'm just going to end now and say one word. So I said that understanding this T-duality led to, lots of progress in string theory and understanding non-perturbative effect, and it led to understanding the whole idea of ADS-CFT correspondence. So what was the next step that people did here, right? So what I argued to you is that there is a symmetry. It's a symmetry in the closed strings, right? So what Joe Polchinski was asking the question is that, is there any difference between closed strings and open strings? And the answer, if you think, is no. There is no difference. The only thing is that the reason why you might expect that heuristically it must be the case is because locally you have an open string, but if you look away from the ends of the open string, the way how open string fluctuates is the same way how the closed string fluctuates. And in fact, there are processes in which two open strings combine and make a closed string. So philosophically, if you wish, there shouldn't be a difference between open strings and closed strings. However, all these ideas that I'm telling you, and precisely the way that the T-duality is this particular parity transformation on the worldsheet, it doesn't quite make sense for the open string to begin with, because on the open strings there is a relation between left and right movers, right? So those relations are imposed on you by the boundary conditions. However, there is a way of thinking about it, and if you think carefully enough, that's what Joe did, you will discover that there is an analog. And I'm trying to tell you that there must be an analog because the open strings shouldn't be very different from closed strings. And if you do that, then you will discover deep range. You will discover a whole new hidden spectrum of states in the string theory that we haven't discussed here, we haven't touched. And the way you discover it by asking exactly the question. So there is this transformation for the closed strings. I'm going to insist that there is an analog of this transformation in the closed string spectrum as well. And you will find out deep range in this way. All right, guys, so as I said, so that's it. So for most of you, I got homework. For those that I didn't, please bring it later today. Okay? All right.